You know, from the screen in your hand to the future of solar power, so much of our technology comes down to controlling light. And that control? It happens at the molecular level. Today, we're diving into a major breakthrough in creating the brilliant, high-purity blue light emitters that are absolutely essential for all of it.
And this is what we're talking about. These are the brand new molecules. They're a whole new class of what we call blue luminogens, basically materials engineered to emit light. Just look at that incredible blue glow. And what's really amazing is that they're shining this brightly in their pure solid form. That's a huge hurdle for materials in electronics, where everything needs to be packed together super tightly. So here's the big question, right? It's one thing to invent a fantastic new material in a lab, but it's a completely different challenge to make it efficiently, cleanly, and without breaking the bank. Could they invent not just a new molecule, but a whole new greener way of making it?
Okay, so to really get why this is such a big deal, we first have to talk about the quest for pure blue light. It sounds simple, but getting it just right is both incredibly important and, honestly, surprisingly difficult.
These little light-emitting molecules, or luminogens, they're the tiny engines powering a huge range of tech. We're talking about the super vibrant and efficient OLED displays in our phones, next-gen lighting for our homes, and even incredibly sensitive biosensors that can spot diseases. And for pretty much all of them, pure blue light isn't just nice to have. It's a critical, must-have ingredient.
The problem is, the way we've traditionally made these molecules has some really serious downsides. The processes often need expensive and toxic metal catalysts, a bunch of extra additives, and harsh chemical solvents. And on top of all that, they can produce a ton of waste. It's just, well, it's not a very sustainable or cost-effective way to do things.
So, how did this research team tackle the problem? Well, they came up with a completely new chemical recipe, one that's just fundamentally greener, smarter, and way more elegant.
This here is their new approach, and it's brilliant because it's so simple. It's a 3-component synthesis. Seriously, think of it like baking a cake. You take 3 common ingredients, you mix them together, and you just add heat. That is it. No toxic catalysts, no harsh solvents, no extra oxidants. It's chemistry at its absolute cleanest. And you don't have to take my word for it. The numbers prove it. When we stack this new method up against the old ones using standard green chemistry metrics, it's a clear winner. The E factor, which is basically a waste ratio, is the lowest, and the reaction mass efficiency is the highest at a whopping 89%. That means almost 90% of the atoms from the starting ingredients actually end up in the final product. So little is wasted. It's just a cleaner, more efficient process no matter how you look at it.
So how exactly does this elegant 3-part recipe actually work? Let's peel back the curtain and take a look inside the reaction itself to see how these simple parts spontaneously build themselves into that complex final molecule.
The whole thing unfolds in 3 main stages, almost like a perfectly choreographed dance. It starts with 2 pieces connecting, then the new molecule folds into a ring, and finally, it locks itself into its stable, light-emitting form. It's pretty cool.
Okay, let's break it down. On the left, you can see the process starts when our first 2 ingredients, which are labeled here as A and 3, come together. This is a classic reaction that forms a new bond, creating our first intermediate structure called I. Think of it as the initial handshake that gets the whole party started.
Now for the really clever part. That straight molecule we just made, that intermediate I, it spontaneously folds back on itself to create the ring structure that you see in I3. That's called cyclization. Then it just sheds a simple water molecule, and you can see it's already starting to look a lot like our final product. And here's the final elegant move. The molecule rearranges itself to become super stable. That process is called aromatization. Then it closes one last ring, which you can see happening between structure VI and 4. This lactonization step kicks out a simple ethanol molecule and, click, it locks the final structure in place. And that's it. That's our finished blue luminogen. So, we've made our molecule with this amazing green method. Awesome. But now for the real test. How does it perform? Just how good is the light that it actually produces?
The answer is exceptionally good. The color purity, how truly blue that blue light is consistently over 80%, with some versions even hitting 90%. Now, in the world of displays and lighting, that is a fantastic number. It totally meets the benchmark for the deep blue emission you need for those next-generation, ultra-high-definition TVs.
And these graphs show us exactly why that purity is so high. You see, what you want is a very sharp, very narrow peak on that emission graph on the right. A narrow peak means the molecule is only putting out one color, a pure, vibrant blue without any spillover into green or violet that would just muddy up the picture.
And this brings us back to one of its most important features. They glow brilliantly in their solid state. You know, a lot of materials are like singers who can only perform solo. When you pack them all together, they just go silent. That's a problem called quenching. But these molecules, they're like a choir. They actually perform even better when they're packed tightly together, which is exactly what you need to build a real-world device.
All right, now for the final critical piece of the puzzle. An amazing green synthesis is really only useful if you can scale it up from a tiny flask on a lab bench to industrial production.
So in chemistry, there's this really important milestone called gram-scale synthesis. It's the moment you prove that your reaction isn't just some tiny laboratory curiosity, but that it has the potential to be a robust, practical process for making real, usable amounts of material. And they absolutely nailed it. The team successfully scaled up the reaction to produce grams of this stuff, and they still got a fantastic 85% yield. This is the ultimate proof that the method isn't just clever, it's practical. It's efficient, it's clean, and it looks like it's ready for the real world. So it's no surprise that the paper's own conclusion is so confident and direct. It really says it all. This isn't just a fascinating piece of chemistry. It's a direct pathway to creating better, more efficient, and more sustainably made optoelectronic devices, the very technologies we all rely on every single day.
And that leaves us with a really fascinating final thought. By just rethinking the fundamental recipe, this research created a better product in a much better way. It really makes you wonder, what other complex and vital materials are just waiting out there, ready to be built using this kind of simple, elegant, and green chemical strategy?